Speed is a relatively simple concept. It's just change in distance over change in time. It's an important concept, too. For example, our country's laws impose speed limits on roads, such as 45 miles per hour. Because of the way speed is defined as change in distance over change in time, these units of miles per hour make sense, at least to an American. So when I read my speedometer on my car and it reads 50 miles per hour, I know that at that moment my speed is exceeding the lawful one, and I should slow down. In other terms, which are slightly more mathematical, I might even say that my velocity at that moment is too large, and I need to decrease it. This might all seem relatively straightforward and unremarkable, since the concept of speed plays such a fundamental role in our culture. But there's actually a paradox at play here, which is at the heart of calculus. The paradox is this: if velocity is defined to be change in distance over change in time, but an instant is a single moment in time, then how could there ever be such a thing as velocity at a single moment? The answer, it turns out, has to do with one of the most fundamental concepts of calculus, the idea of a limit. To understand this paradox better, let's work in the language of functions to try to describe the situation more precisely. Suppose, for example, that we've worked out the position function of our car to be s of t equals t squared, where we're measuring time t in hours and position s in miles. For example, at the time t equals 0, the car is at position s equals 0, meaning that the car has not traveled anywhere. However, after 1 hour, which corresponds to the time t equals 1, the car is now at s equals 1, meaning that it has traveled 1 mile. Admittedly, such a car would be going very slow, making this example a little bit artificial. Indeed, the average velocity of the car over that hour is just 1, because the car achieved a change in distance of 1 mile over a change in time of an entire hour. But, as time progresses, the car does speed up, and by the next hour, that is, at time t equals 2, the car is at s equals 4, which means that the car has an average velocity of 3 miles per hour during this interval. But our concern is not necessarily how to compute an average velocity. We'd like to try to understand what is meant by instantaneous velocity. Let's try to do so at a specific time, say t equals 25, that is, after 25 hours. Now, hopefully you don't ever have to drive continuously for 25 hours, but as we've decided, our example is a little bit unrealistic in terms of the actual numbers involved, so we'll just continue working with this in mind. So, we'd like to know what the speedometer would read after 25 hours, if our position function were described by s of t equals t squared. Now, because we're interested in instantaneous velocity, we don't have any change in time to work with. This is somewhat problematic since a change in time is literally the denominator of the definition that we understand for velocity. As a second best attempt, rather than letting the change in time be equal to 0, which makes the fraction of velocity cease to exist, let's instead make the change in time very small and close to 0, say 0.1 hours, for example. Specifically, let's set t1 to be 25 for the time we're interested in, and let's set t2 to be 25.1 for a short while after the time we're interested in. If we compute the average velocity between these two times, then we'd obtain an average velocity which should be fairly close to the instantaneous velocity we seek. So we compute for these numbers, and the change in distance is given by 25.1 squared minus 25 squared, which is 5.01. And we are dividing this change in distance by a change in time of 0.1 hours. What we obtain then is an average velocity of 50.1 miles per hour, which should be close to the instantaneous velocity we seek. That is, it should be an approximation. But the keen observer will note that we could have done our approximation even better. In particular, we could have taken a smaller change in time. After all, a change in time of 0.1 hours is still 6 entire minutes, which isn't very small. Instead, let's try a change in time of 0.001 hours. For this, our new t2 should be 25.001, and we'll compute in the same way as we did before to obtain an average velocity now of 50.001 miles per hour, which, again, is an approximation of the instantaneous velocity we seek. Now again, a keen observer might suggest that our approximation is still not good enough, and we could have done better. Maybe this observer suggests we try the changes in time of 0.0001 or even 0.00001. We could do as the observer suggests, plotting the resulting average velocities in a table, but notice that our table will never satisfy this keen observer. So let's stifle his complaints by covering all possible changes in time at once. In other words, let's call the change in time h, where we are to think of h as being a very small number. In the first example above, h was 0.1, and for the second example, h was 0.001. But now h will be arbitrary and will compute in the same way as before. In terms of our old notation, t2 should now be 25 plus h, and we can compute the average velocity by computing the change in distance over the change in time. After expanding in some algebra, we obtain an average velocity of 50h plus h squared all over h. As long as h isn't 0, we can divide by it, so let's do it, and we obtain an average velocity of 50 plus h. Notice that this fits with the observations in the table we made above, where, by taking h equals 0.1 for example, we found an average velocity of 50.1. But each of these numbers in the table is just an average velocity, and each of these numbers, 50 plus h, is an average velocity too. What we really want is the instantaneous velocity. For this, it seems natural to say that the instantaneous velocity is the number we get when we take h closer and closer to 0, that is, by making the change in time arbitrarily small. From our calculations we just did, it's clear that by taking h closer and closer to 0, the value of the velocity gets closer and closer to 50. Putting everything together then, we realize that we've arrived at an answer to our question, namely, the instantaneous velocity at the time t equals 25 should be equal to 50. The important thing is that this number 50 is not really a velocity per se, but rather a limit of velocities, where the limit is obtained by making the change in time closer and closer to 0. In particular, it is the limit of 25 plus h squared minus 25 squared all over h. And we're taking this limit as h tends to 0. With this notation, it's clear that the denominator is tending to 0 because h is, but it's also true that the numerator is tending to 0 as well, because as h goes to 0, so does the numerator. What the instantaneous velocity is then is not really a velocity at all. It's a type of competing limit of two quantities, both of which are tending to 0, but in such a way that their ratio tends to a finite number, which we call the instantaneous velocity.